Research in the Kretzschmar group at the City College of New York evolves around patchy particle and chordal assembly. We have three major research areas that I want to briefly introduce to you. The first one is Janus and patchy particle synthesis and assembly. What is a Janus particle? Here you see a scanning electron microscope image of Janus particles. They're spherical particles that have a coating on one side of their surface that's different from the base particles. So for example, the base particle here is polystyrene and the coating is iron oxide. In addition to Janus particles, we have also developed methods to make patchy particles, and that's briefly described here. The technique that we have developed is a glancing angle deposition technique, where we angle the source with respect to our particle layer, and as a result of that, we get patches of different sizes. In addition, when we add a stamping procedure in between, we can make patches on two sides of the particle, and we can again make them in two different sizes or more sizes. The last version here is where we evaporate from two directions on one side of the particle and get overlapping patches. In addition to particle preparation, we also study the behavior of these particles. For example, when we have suspensions of these particles in aqueous solution, we are drying them on surfaces to understand what kind of patterns they form. And this is a reminder of the coffee stain problem that has been investigated for a long time. In addition to convective drying, we also look at field assembly. And so in field assembly, we are taking these particles, putting them in an aqueous solution and apply a magnetic field. And when these particles are exposed to a magnetic field, you can see that the caps align such that they form this string of particles. And if we now change the electric field that's parallel to the magnetic field here, we get this behavior. The chain expands and contracts and expands and contracts. And so these particles can be quite functional and used in applications, for example, as muscles. So this leads me to the second area of research that we're interested in, and that is nanomaterials and energy research. You will see that Janus particles play a role here as well. But initially we looked at dye-sensitized solar cells, and here we studied the following problem. Dye-sensitized solar cells usually have porous titanium dioxide and zinc oxide electrodes that are made of nanoparticles. The problem with these electrodes is that the electron pathway is very tortuous, and very often electrons don't even make it to the collecting electrodes. To increase their efficiency, we have made inverse opal structures out of zinc oxide and titanium dioxide, and here electrons show a much higher efficiency of being transported to the collecting electrode. This shows an image of an inverse opal structure taken with a scanning electron microscope. More recently, we have looked at ultra-small quantum dots as sensitizing materials for these solar cells. Ultra-small quantum dots are made of cadmium selenide, and they have a nominal size of 1.5 nanometers. They have an interesting behavior in that they absorb in the UV, which is shown here by the blue light, and they emit white light, which is shown here by the red light line. And so the white feature you see here, this is caused by emission of quantum dots, ultra-small quantum dots. And we have put them into into solar cells, and we have shown that they are viable even after being put into these solar cells. Now let's get back to the active Janus particle systems. So Janus particles made of polystyrene or silica and a platinum coating. When they are put into hydrogen peroxide water solution, the platinum will decompose the hydrogen peroxide into oxygen and water, and the oxygen creates a gradient around the particle, which causes the particle to be moving autonomously. And so what we see is, after we study this behavior of particles near wall, is that they show Brownian and enhanced Brownian motion, so they're guided by the wall. And we have also looked at these particles at liquid-liquid interfaces, and we study their behavior at these interfaces. This leads me to the last research area, Janus particles at interfaces. Here we have looked at particles at all water interfaces and air-water interfaces. You see an MD simulation here, which has two phases, a yellow phase and a blue phase with an interface, and a Janus particle that has two sides, and you will see eventually the particle jumping to that interface and staying stable at the interface. It just jumped. So here you can see the yellow air side lined up with the yellow fluid and the blue side with the blue fluid. We have also looked at these particles at the air-water interface using a Langmuir trough, and here you will see that as we are compressing these barriers, so as we are moving these barriers closer to each other, we are compressing this particle layer. The particle layer gets more and more dense, and eventually you will start to see it forming folds, just like a fabric would form a fold. Note that this video is sped up 16 times, and you will see that very soon you will start to see the wrinkling of the surface, and then you now the wrinkling starts, and then you will start to see folding, and you see very deep folds. And so as these folds are formed, the particles stay in the interface, but the interface gets actually deformed. So I hope what I've shown you today gives you an idea of what we do in our group and you find it interesting.